Our goal at Tidal Energy is to harvest the clean energy generated by waves into useful energy used in various applications. We have been presented with the problem of designing a linear generator that aids in converting these low-frequency waves that generate a lot of force into more useful energy without resorting to rotary generators. The design will be providing for marine applications as the priority, with the goal of being environmentally sustainable through the usage of clean, freely available energy from ocean tides. The key requirements for attaining our goal is that we shall design a generator that converts tidal energy into electrical energy. In addition to, we shall achieve a conversion efficiency of above 25% as tasked by our industry supervisor, and we shall design a physical prototype as a proof of concept.
So after defining our key requirements and doing some prior research into different types of linear generator technologies that are currently being employed, our team created a preliminary selected design. And we created a sketch of this along with a list of some of its key features. So the first feature is that it's fully floating, meaning that it won't be anchored to the ground, to the ocean floor. Making this a more portable device than what is currently on the market. The second attribute is that it'll be a point absorber with a spring. The third would be that it uses a permanent magnet to convert the mechanical motion into electricity, and the buck boost converter will be used in the energy and power conversion process, along with a LabVIEW code to output our results. On this side we have our mechanical design, and on the left-hand side of the screen was our first iteration of our SolidWorks model. And how it works is that when the device is in operation, a drag force is applied to the bottom plate, which stabilizes itself, while the upper part will float on the surface of the ocean, or in this case, the testing tank, to mimic the motion of the wave. And as the wave rises and falls, the spring in the center on the center rod will either compress or stretch, and upon doing so, the center rod attached to it will oscillate the permanent magnets that come off of the branches on the side and go through the copper coils. And through Faraday's law and electromagnetic induction, an EMF voltage will be induced in the coil where the electrical energy will come from. And in the right-hand side of the screen, we have our updated SolidWorks model, which consists of 3 magnetic coil branches instead of 4, a reduced height of our mechanical device to increase the stability while it's on the surface of the wave. We also have a guiding center tube for the spring to go through so that it's more stable as it's on the surface of the wave. And we added a cake pen as our drag element on the bottom to be maintained under the water, along with a pool noodle as our flotation device on the bottom of the top floating mass.
This is a closer look into the electrical design of our system. It possesses 3 distinct blocks, namely the electromagnetic coils, the AC to DC rectification block, and the DC to DC converter block. The electromagnetic coils induce an alternating voltage from the mechanical motion of the waves. The rectifier changes that alternating signal into a constant voltage signal. And finally, the DC to DC converter adjusts the magnitude of the constant voltage signal for various applications. As mentioned before, a buck boost converter would be appropriate for this device on a larger scale because it steps up or steps down the input voltage, providing more flexibility to control the output. However, we have decided to test our prototype with a step-up converter instead, since it operates at smaller voltage scales.
So in this video clip, we have footage from our mechanical testing in the wave generator testing tank. And during this procedure, we obtained data about the relative heights of the top and bottom masses by varying the frequency of the waves so that we could get constructive interference and get the maximum displacement of the top mass. Then this displacement information was passed along to our electrical team so that they can use it in their design.
Here is a quick demonstration of how the electrical system works. This is only a manual replication of how the waves would oscillate the magnets. So as you can see, when only one coil is used, the LED is not lighting as brightly compared to when all 3 coils are used. This is because all three voltages are being supplied to the converter, and this basically emulates how our device would convert the mechanical energy into electrical energy.
Regarding the electrical testing, we were able to use the data from our mechanical team to develop an optimized coil which could produce the most amount of voltage using the displacement data that we received. So we tested by using magnets to excite the coils and measuring the voltage output that they produced. We found that the air gaps between the coil windings were causing significant inefficiencies. So we used the resources in the Bergeron Mechanical Lab, the lathe, and were able to reduce those air gaps and really improve the efficiency of the output voltage of these coils. And we were able to achieve a 77% calculated efficiency. The requirement was 25%, so we were above that. We exceeded that goal. We would have been able to have more accurate testing results if we had the time and the ability to assemble the entire device and measure it using current probes. However, we didn't have access to current probes, so that was a challenge because we had to use voltmeters to measure the output and calculate the efficiency. However, these results were very encouraging, and we think that we could at least meet or exceed the efficiency requirement of this project according to these results.
Our next steps entails the integration of both the mechanical and electrical system to form the overall system, perform additional testing for optimization, and to further collaborate with our industry partner, Panoplo, to refine the design and shift to large-scale production.
Our research shows that there are no existing maritime linear generators that are able to perform the way our design does. And that means that most of the existing products are fixed to the ocean floor, and our device is anchorless, which makes it very easy to use and versatile. And furthermore, we're also able to achieve a very high efficiency out of this product. So we think that the impact this could make, it may be able to revolutionize the way energy is harvested from tidal waves.
The lessons learned over the course of this project are that it's really important to define the requirements and objectives of the project early on as a team. That way everybody is working together towards a common goal over the course of the project, and to often reference back to the requirements at every gate of the design process so that they can be updated when new information becomes available. The second lesson is to perform comprehensive design calculations, especially in the critical design stage, before components are ordered so that unexpected costs can be prevented and avoided. And the last item that we learned is that it's really important to have an open channel of communication among our team members as well as with our academic and industry supervisors.